Hello, everybody. So I just want to try to convince you that Planck also unveils the Sonia-Soldovit effect. So for this, we are going to present you the Planck all-sky contour parameter map, his power spectrum and high-order statistics. This is based, This is based on the analysis of the Planck, Planck 2013 result, paper 21, and to go through the talk, I will first discuss the reconstruction and calculation of the Planck Y map. We'll go through the power spectrum analysis we have performed to characterize that map, and then give some hints on the high-order statistic of the maps and how this impact the cosmology. So the contour parameter map was obtained using component separation algorithm. In particular, we adapted those to the ESTEC signal, and we use internal linear combination algorithm, the NILC and MILCA algorithm. We use constraints both on electromagnetic spectra to preserve the TSZ effect and to remove the CMB. And we use also simultaneous separation in the spatial and the spectral domain. That was to cope with the fact that clusters are particular objects, like mainly punctual. So we use the HFA channel from 100 to 850 GHz, and for the later channels, in order to avoid point source contributions, we use only the very large angular scales. We put all the maps to a common resolution of 10 arc minutes, and we validated the whole process on the full focal plane simulations. I just want to notice that the same algorithm, MILCA and NILC, were used for the PIP papers, and for example, for the coma cluster and the cluster measure analysis that will be presented later in the week by Barbara. So here you have the Planck contour parameter map. This is an also view of the map. So this is north and south poles. And the map has been filtered here for illustrative purpose. So you can see some of the clusters, which show up as little dots here, in particular known clusters like the coma cluster here, and the Virgo cluster. Yeah, I just draw your attention to the fact that this is in the Y map units, multiplied by 10 to the power 12. Sorry, 10 to the power 6. It will be 12 for the spectrum. So we can now compare the map with previous statistics from Planck. In particular, we can compare it to the Planck ESTEC catalog. So here you have a draw of a zoom of the map, where you can see the cluster here very, very well individually. And what we did is just to use independent components method to detect class in the Y map. In particular, we use two of them, set extractor to detect the point sources, and then the multi-match filter to compute the flux on the Y map. And also we use the Mexican half wavelet to detect clusters and set extractor to complete the flux. So you have here a plot showing the integrated contour parameter maps for both the cluster detected in the Y map and the cluster in the Planck ESTEC catalog. So you can see that we have a very good correlation of 1 between the two. And the good thing about that is the number of detected cluster is consistent with the what in the catalog, and the flux is also consistent with that. The following thing we did is just to check on foregrounds. For this, we applied the same component separation to the FFPC simulations and look at the results. So we compute the power spectrum between the first and last maps. These are the maps which are computed from the first part of the rings of the Planck rings and from the last part of the Planck rings. So the good thing about that is that noise is uncorrelated between the two, and then we can reveal systematic, for example. So you have here the power spectrum and a function of multiples. So this is the power spectrum of the Y map. So it's in units of contour parameter times 12 to the 12. And so you can see different components. So you have here the ESTEC signal in red in the maps. You have here the contribution from dust, thermal dust emission, and in green you have the contribution from CAB, and in cyan you have the contribution from point sources. So we have at the end that the ESTEC signal is expected to dominate in a range from 100 to roughly 800 in multiple. So in order to improve that, what we did is try to enhance the signal to noise. For that, we first mask 50% of the sky to remove contamination from thermal dust. So we mask the brightest part of the sky. And we use also a mask to mask strong point sources. And finally, we use a refined modeling of foreground based on physical interpretation that I will present just afterwards. So you also have here in the plot what is the noise, typical noise of the map. You can see that the detection is difficult, but it is possible to do it. So the other thing I just want to show you is that once you model the different components, so thermal, as said, cluster, CIB, and point sources, because the mask removes most of the thermal dust. So you have something like that, which three parameters that we have left here. One is the amplitude of the CIB spectrum, and the other one is the amplitude of the point sources. So for the thermal set, we use a typical two-halo model using the Tinker et al. Mass function that Marion presented before, Arnaud et al. Profile, and a bias as discussed by Marion before. So this model is exactly the same that the one in the cluster number count. So we wanted to preserve coherence between our analysis. For the cluster CIB, we did something similar. So we used the model coming from the CIB paper that will be presented by Gillen's talk afterwards. And we use a model which is sorry, it's not Gillen anymore. That should be presented by Gillen's. So this model is based on the best fit frequency, auto, and cross power spectra for the 6 HFI bands, and we accounted for 5% uncertainty on those. Finally, for point sources, we did also self-consistent as well, which was uses number count model from the radio sources from Touchy et al. And from Wettermann et al. So after all, taking into account uncertainties in these two models, we use something like a Gaussian prior for the amplitude of the point sources on the CIB, which 50% uncertainty. So you have here the power spectrum and the fashion of multiple. So in black is the original power spectrum of the map. In red you have the power spectrum after subtracting foregrounds and the different foreground components as before, the CIB, radio, and infrared point sources. So you can see that we have, as expected, a very well detection of the TSZ power spectrum between 100 and 800 in multiple. Actually, if we just look at it more closely, so you can see that the detection is finally from something like equal 52 up to L equal 10,000, for which we have the first measurement of the large angular scale of the HC power spectrum. I just plot here the ACT and SPT data just for comparison. What you have here is our best fit model in red, and also for comparison in blue, I just plotted the best fit model that Marion presented before from the cluster number counts. You can see that both of them are consistent, was presented by Marion before. I also plotted here the CMB template that was used for the CME analysis, sorry, the TSZ template that was used for the CME analysis, presented by George yesterday. And you can see that after scaling, it's also consistent with the data. Something which is also interesting to see is that the data here is just well represented by a power law. One of the questions we can ask ourselves is, what happens to the already observed clusters? So what is the power spectrum of the resolved cluster? So for that, what we did is to simulate the clusters using the redshift and the quantum parameter map deduced from the cluster sample. And we did a rather complicated analysis, which is shown in this figure. So you have here the power spectrum and fashion of multiple of the original map in black, of the clusters, resolved cluster here in orange after simulation. And the one you have in red is actually the power spectrum of the map, of the quantum parameter map, once you have masked the cluster. So we mask the cluster, we take the power spectrum, and just by taking the difference of the black and the red, you get the green curve, which will be the power spectrum of the resolved cluster. So you can see that the expected power spectrum and the measured one are really consistent. In the same way, we can try to do the cross-correlation between the simulated map of the clusters and the quantum parameter map. And this is what is shown in the blue points here. And you can see that the free estimate of the cluster emission are consistent. The other thing you can see is that with respect to the total signal, we can not only represent the full measured power spectrum for the TSZ with the resolved clusters. So this push up to do a cosmological analysis of the power spectrum. So we use an MCMC analysis as before using only 4 parameters here. So sigma 8, omega m, the amplitude for the CIB, and the amplitude for the power for the point sources. So you have here the constraints. And the only thing you really need to look here is that we don't have any degeneracies between the, well, we don't have degeneracy, actually. We have a strong degeneracies between sigma 8, okay, if I can follow it. Okay, I can't see it anymore, but okay. We have a degeneracy between sigma 8 and omega m, which we actually parameterize by combination of the 2 parameters. So finally, what we actually measure is sigma 8 omega m, and we get a result which is actually consistent with the one presented by Marian before. One of the questions we can be asked for is, what is the physical model dependent of this measurement? For this, we trace the power spectrum as a function of multiple for different models in the literature. So in red, you have our best fit model. In blue, the number count best fit models. And then you have different models, for example, the analytical model from Cho et al. You have the full numerical simulation model from Battaglia et al. So this is the 2012 model. So just Nick sent us 2012, and we will update the figure soon. And we also have semi-analytical and numerical simulation models from Track, Boat, and Striker. So we have 2 of them, one for the one, assuming just adiabatic fluctuations and no feedback and no star formation. This is number 1. And number 2, for which we assume a standard model with star formation and feedback. So you can see that there is a large spread of model here, which makes in us that the exact constraint we have in the cosmology will depend on the physical modeling. So this is an important thing that we have to keep in mind and check on it. So the other thing we did is just a high-order statistic analysis of the map. So for this, we use the 1D probability distribution function. So before doing that, we filtered the maps as in the same way that we did before for illustrative purpose. And we computed the 1 PDF of the maps. So we did both for the simulation and from the Planck map. So here you have the 1 for the simulation. So this is the probability distribution function as a function of y. And you can see that we have different components. Where you have that signal that show up with a positive tail. We have radio sources which show up like negative tails, and CIB, cluster CIB and noise that show up like kind of a Gaussian component. So from this you can see that we are really dominated by the SZ signal here. So if you look at now the one for the Planck map, just is shown in this figure here. So you can see we can recover the negative tail from the point source, which is marginal. You can see the Gaussian part coming from noise plus CIB clusters, and then the very well-determined TSC tail, from which we can once again try to derive constraints on the cosmology. For this, what we did is to compute the unnormalized skewness. So we used the analysis from Wilson et al., same type of analysis, and comparing to simulations, we can derive constraints which are actually consistent with the one we obtained before. A similar analysis went down from the BS spectrum. So we computed the BS spectrum for various configurations, and this time we really use it directly on the original map. So you can see here, against for the simulations and from the Planck data, so you have the BS spectrum for the equilateral configuration as presented yesterday by Sabino, as a function of multiple L. And here you have the foreground component for the CIB, LZ and thermal dust. Sorry, CIB, free and thermal dust. And here you have the expected TSZ signal. So now, if we go to the map, to the Planck map, you can see that this is the measured Planck BS spectrum, both for the Milka and NILK. So we have a good consistency between the 2 methods. This is what would be expected from resolved clusters in blue. So we have for the first time a good measurement of both resolved and resolved clusters, and maybe diffuse emission from the TSZ signal from the BS spectrum. And this is, for example, what we have for the TSC for the FFP simulation. So comparing our measurement to the model, we can also derive constraints on sigma 8, which once again are consistent with what we measured before. So I just come to conclusions. So I think we can say now that Planck has obtained for the first time, an all-sky map of the control parameter of the TSZ signal. The cluster properties in the Y map and the cluster sample are consistent. We have been able to determine the power spectrum over a large angular scale range going from 3 degrees to 10 arcminutes, so correspond really to L50 to L1000. The power spectrum and the high order statistic of the map are consistent with the TSZ origin of the signal, so I think this is quite clear from the analysis. And we have been used these statistics to set constraints on cosmological parameters. So these constraints are consistent within, I will say, TSZ analysis presented by Marion before. And we have a discrepancy with the CMB, which is roughly the same at the 2.7 sigma level. That, as I said before, and Mario just discussed, can be accounted for by model dependence in the physics of clusters, or more exotic, like having an extra neutrino. So I will stop here. Thank you.
Since you can see, you can map the Y parameter and take out the rich clusters, do you have any better sensitivity than all sky X-ray surveys for looking for missing baryons?
Well, what we can measure is the full power spectrum, and we can measure individual clusters, as before I said before Marion. And so we are measuring the overall picture. We cannot locally quantify.
You get statistics, but not in real space.
Well, we don't have the real space statistics. We have the full thing.
You mentioned the case of an extra neutrino, and so did the previous speaker. Reactor experiments show the possibility of electron volt masses for neutrinos. This is not coming out of the Planck analysis. How is this treated in the Planck community?
Okay, so I think this is probably not a question for me, but rather from George or Marion. But it's true that for this analysis, we didn't cope with this. I know there are analyses from Ross et al. That try to use massive neutrino to account for the discrepancy between HC and CMB using other models. But this is not the whole story. You can also change scaling properties or mass bias to reproduce the same result. So I don't think we can conclude on that from the ESTEC signal directly.
Any other question? Okay. Then we thanks again Juan for the talk.